So it turns out that there are particles, such as gluons, that can interact with the virtual particles, virtual versions of themselves. And that's because the strong nuclear force is very different from the electromagnetic force. And it's also a major problem in physics because we don't have an easy way to describe how quarks and gluons interact because of all these diagrams that involve these virtual particles to infinities. And that's what you hear about renormalization and all of these efforts being made to clean up the theory, because it gives an infinite number of diagrams, an infinite number of virtual particles interacting with virtual versions of themselves, on and on and on. And it's a big mess. And basically, the exciting thing here is that's kind of a breakdown in the theory, and it shows that, there's a lot more that needs to be done in this field, especially in quantum chromodynamics, the study of how nuclei, what makes nuclei, because we see nuclei, protons and neutrons, and in the 1950s they thought that they were fundamental particles, or they suspected they might be, but it turned out that that's not the case when you crash these particles into each other at high velocities and create vast energies. They interact in ways that shows that they're made up of other things. So they're actually composite particles, protons and neutrons. They're composed of quarks and gluons. And the gluons are like essentially force carriers for the quarks, but they don't interact in nice ways that are easy to calculate. Gluons can couple to other gluons and form these like gluon balls, glue balls they call them, and we don't have a solution at all for how atom nuclei interact and how these are created. Like, why is the mass of the proton what it is? Why is the mass of the neutron what it is? We don't have a good theory for that right now. That's called low energy quantum chromodynamics. And I just wanted to illustrate that because when I say something like a virtual particle can't interact with the real version of itself, that's true in quantum electrodynamics, but it may not be true. It isn't true, in fact, in other branches of quantum field theory, like the quantum chromodynamics and the strong nuclear force and things like that. So I just wanted to clarify this point that I made, because it was in regards to light interacting with an electric or magnetic field, the magnetic and electric fields being made up of virtual photons. So it turns out it's not so simple when you talk about other forces like the strong nuclear force.